Hello. In the last two lectures, we have covered various concepts for parallel plane waveguide. Today, we'll extend those concepts to rectangular waveguide. After that, we will see some applications of waveguides. So, let's begin with rectangular waveguide. In rectangular waveguides, there are four finite metallic plates, of which two metallic plates are in YZ plane and those plates are separated by a distance a in x direction, and the two metallic plates are in xz plane which are separated by a distance b in y direction. Now, as we have discussed earlier that to find the longitudinal field we need to solve the wave equation or Helmholtz equation. So, Helmholtz equation for electric field is del square E plus k square E is equal to 0, or we can write it as da by square Ez by da by x square plus da by square Ez by da by y square plus da by square Ez by da by z square plus omega square mu epsilon Ez equal to 0. Since in rectangular waveguide waves are confined in two direction, one is in x direction, other one in y direction, and the third direction is the direction of propagation. So, the field varies in all the three directions x, y and z. So, we can write longitudinal electric field Ez as a function of x, y and z, which is equal to function of x into function of y into function of z. Now, put this Ez in this wave equation. So, we will get y into z double derivative of x plus x into z double derivative of y plus x into y double derivative of z plus omega square mu epsilon x, y and z is equal to 0. Now, divide this whole equation with the x, y and z, then we will get this equation: double derivative of x divided by x plus double derivative of y divided by y plus double derivative of z divided by z is equal to minus omega square mu epsilon, or we can write it as k square. Since these x, y and z functions are independent of each other and this term k square is a constant, so the each term in this equation must be a constant. So, we can assume double derivative of x divided by x is equal to minus kx square, and double derivative of y divided by y is equal to minus ky square, and double derivative of z divided by z as minus beta square, or we can write it as plus gamma square. So, in gamma if alpha is 0 then we will get minus beta square, and the signs of these constants are taken as negative for propagating wave. And if we take positive signs of these constants, then the solution of these type of equation will be a exponential function that will represent a attenuating field or a non-propagating field or a evanescent field. So, for propagation of the waves the negative signs are considered. We will get these type of second order differential equation. From here we can get x, y and z. So, x comes out to be C1 cos kx into x plus C2 sin kx into x. Similarly, y comes out to be C3 cos ky into y plus C4 sin ky into y, and z comes out to be C5 e raised to gamma z plus C6 e raised to minus gamma z. Now, by putting these fields in this equation we will get the longitudinal field Ez. So, Ez will be multiplication of these three. So, it is C1 cos kx into x plus C2 sin kx into x multiplied by C3 into cos ky into y plus C4 sin ky into y multiplied by C5 e raised to gamma z plus C6 e raised to minus gamma z. The term e raised to gamma z in this equation represent the propagating wave in negative z direction, and the term e raised to minus gamma z represents the wave propagating in the positive z direction. But we have assumed that wave propagation is there in positive z direction. So, this term should be 0. So, C5 will be 0, and the electric field Ez reduces to this A1 cos kx into x plus A2 sin kx into x into this A3 cos ky into y plus A4 sin ky into y into a raised to minus gamma z. Similarly, we can derive longitudinal magnetic field Hz, which will be this. If we know Ez and Hz, then we can derive the transverse fields Hx, Hy, Ex and Ey as we have derived for parallel plane waveguide, and the constants are same as before. There is only one difference, which is h square is equal to kx square plus ky square, because the wave is confined in both x and y direction. Now let us see how these fields vary in different modes in a rectangular waveguide. So first start with TEM mode, which is transverse electric and magnetic mode, in which the electric and magnetic fields are transverse to the direction of propagation, and in the direction of propagation there is no electric field and magnetic field. So Hz is equal to 0 as well as Ez is equal to 0. Now if we put these values of Hz and Ez in the field equations, then we will get Ex equal to 0, Ey equal to 0 and Hx equal to 0 and Hy equal to 0. That means all the field components are vanished. So there will not be wave propagation in the waveguide in TEM mode, or we can say rectangular waveguide does not support TEM mode of propagation. Now move on to the next mode, which is transverse magnetic mode, in which the magnetic field is transverse to the direction of propagation, or we can say magnetic field is 0 in the direction of propagation. So Hz is 0 and Ez is non-zero, and as we have derived earlier that the longitudinal electric field will be Ez is equal to this. Now we need to apply boundary conditions on this electric field. And what are boundary conditions? Boundary conditions are that the tangential component of electric field should be 0 at the conducting boundaries, and in the rectangular waveguide we have 4 conducting boundaries. One is at x equal to 0, another one is at x equal to a, and other two are at y equal to 0 and y equal to b. So put x equal to 0 in this equation. So we will get a1 cos 0 plus a2 sin 0. Sin 0 is 0, cos 0 is 1. So we will get a1 into something. Now equate this to 0. So we will get a1 is equal to 0. Similarly, put y equal to 0 in this equation. Then we will get a3 cos 0 plus a4 sin 0, and from here we will get a3 is equal to 0. Now put the values of a1 and a3 in this equation. So Ez reduces to E0 sin kx into x into sin ky into y e raised to minus gamma z. Now apply the other two boundary conditions, which are at x equal to a, Ez equal to 0, and at y equal to b, Ez equal to 0. So if we put x equal to a in this equation, then what will happen? Sin kx into a, that should be 0, which makes kx into a is equal to m pi, where m is an integer. So from there we will get the value of kx is equal to m pi by a. Similarly, if we put y is equal to b in this equation, then we will get sin ky into b, and we need to make that to 0. So ky into b will be n pi, where n is an integer. From there we will get ky is equal to n pi by b. Now put these values of kx and ky in this equation. So Ez will be E0 sin m pi by a into x sin n pi by b into y e raised to minus gamma z. So this is the longitudinal electric field in TM propagation. Now let us see what are the propagating and non-propagating modes in TM propagation. So as we know Ez and Hz, so we can derive Ex, Ey, Hx and Hy. So these are the field equations for these transverse components. Now if we put m equal to 0 and n equal to 0 in these equations, then the mode will be TM00 mode. So if we put m and n equal to 0, then this will be sin 0 into sin 0. So Ez will be 0, Hz is already 0. Similarly, Ex will be 0 into something 0, and Ey will be 0, and like this. So all the field components in TM00 mode are 0. So there will not be propagation of electromagnetic wave. Similarly, if we put n equal to 0 and m can be anything, then this will be 0. If we put n equal to 0, then we will get sin 0 here. So Ex is 0. Put n equal to 0 here, then 0 into something, Ey will be 0. Similarly, Hx 0 into something, it will be 0. Same way, Hy is equal to sin 0, which is 0. So this is how all the component will be 0 in Tm M0 mode. Similarly, for Tm0n mode, where m is 0 and n can be anything, all the field components will be 0. So for these three modes, there will not be any propagation of wave. So these modes are called as non-propagating modes for rectangular waveguides. If we put both m and n greater than or equal to 1, then these fields will not be 0. So there will be propagation of electromagnetic wave. So Tm Mn modes are the propagating modes in rectangular waveguide. Now let us see how field varies in propagating modes in Tm propagation. This is the example for Tm21 mode. This graph is for xy plane. This is the variation of fields in yz plane. So as you can see from this, there is a 2 half sinusoidal variation of the fields in x direction, and there is only 1 half sinusoidal variation of the fields in y direction. In general, in Tm Mn mode, there is m half sinusoidal variation of fields along x direction, and there are n half sinusoidal variations of the fields in y direction. So now let us see in these graphs. In the first graph, along x direction there is 0, maxima 0. This is a half sinusoidal variation along x direction, and along y direction maxima 0, maxima. This is also a half sinusoidal variation. So this mode is a Tm11 mode. Similarly, in this there is 0, maxima 0 in x direction, and in y direction there is maxima 0, maxima 0, maxima. So this is 2 half sinusoidal variation of the fields. So this mode is Tm12 mode. Similarly, in this, in x direction there are 2 half sinusoidal variation of the fields, and in y direction there is only 1 half sinusoidal variation of the field. So this is Tm21 mode. And similarly for this, along x direction there is 3 half sinusoidal variation of the fields, and along y there is only 1 half sinusoidal variation of the fields. So this corresponds to Tm31 mode. All these 4 plots are in xy plane. Now let us move on to the next mode, which is TE mode, transverse electric mode, in which the electric field is transverse to the direction of propagation and there is 0 electric field in the direction of propagation. So Ez is equal to 0 and Hz is not equal to 0. And as we have discussed earlier, that the general solution for Hz is this one. So we need to apply boundary condition for this, and boundary conditions are the tangential component of electric field should be 0 at the conducting boundaries. There are 4 conducting boundaries: x equal to 0, x equal to a, y equal to 0 and y equal to b. For 2 boundaries x equal to 0 and x equal to a, there are 2 tangential component Ez and Ey. Ez is already 0, so we need to make Ey is equal to 0. To make Ey equal to 0, first we need to find Ey. So how we will find Ey? Since we already know Ez and Hz, so we can find Ey in terms of Hz and Ez. That will be Ey is equal to j omega mu by h square dabba Hz by dabba x. So if we need to make Ey equal to 0, then dabba Hz by dabba x should be 0. So put this boundary condition at x equal to 0, dabba Hz by dabba x is equal to 0. Then we will get A2 is equal to 0. Similarly, for y equal to 0 and y equal to b, the tangential components are Ex and Ez. Ez is already 0, so we need to make Ex equal to 0. So write Ex in terms of Hz. Ex is minus j omega mu by h square dabba Hz by dabba y. If Ex is 0, then dabba Hz by dabba y will be 0. So if we differentiate this with respect to y, then we will get a3 sin y plus a4 cos, and if we put 0 here, then we will get a3 sin 0 plus a4 cos 0. So this term will be 0, and then we will get a4 into something, and then we need to make that equal to 0, then we will get a4 equal to 0. If we put these two conditions here in Hz, then Hz will be h0 into cos kx into x into cos ky into y e raised to minus gamma z. Now apply the other two conditions. The third one is at x equal to a, ey equal to 0, or we can say at x equal to a, dabba hz by dabba x is equal to 0. So sin kx a will be 0. From here we will get the value of kx, which is m pi by a, where m is an integer. Similarly, if we apply this condition, then we will get ky is equal to n pi by b. Now by putting kx and ky in this equation, we will get hz is equal to h0 cos m pi by a into x into cos n pi by b into y e raised to minus gamma z. So this is the longitudinal magnetic field in TE mode. Now let us see what are the propagating and non-propagating modes in TE propagation. So we know Hz and Ez, we can find transverse fields Ex, Ey, Hx, Hy in terms of these two. Now if we put m equal to 0 and n equal to 0 in these field equations, then what we will get? Ez is already 0, we will get Ex equal to 0, Ey equal to 0, Hx equal to 0, Hy equal to 0, and Hz is not equal to 0. Since all the transverse field components are 0 in this mode, so wave will not propagate in this mode. So TE00 mode is a non-propagating mode in TE propagation. And if we put m equal to 0 and n can be anything which is greater than 1, then Hz, Ex and Hy will not be 0, and if we put n equal to 0 and m can be anything which is greater than 1, then Hz, Ey and Hx will not be 0, and because of this there will be propagation of the waves in these two modes. Similarly, if we put m is greater than or equal to 1 and greater than or equal to 1, then there will be propagation of the waves. So these three modes TE0n, TEM0 and TEMN are the propagating modes for rectangular waveguide. Now let us see how fields vary in TE mode. So as you can see from this is the x-axis, this is y-axis, and this is the direction of propagation. As you can see from this figure that in x direction there is half sinusoidal variation of the field, because at this point 0 field is there, here it is maximum, here it is 0. So there is half sinusoidal variation along x direction, and along y direction there is no field variation. So this will be TE10 mode. Similarly for this, in the x direction there are two half sinusoidal variations of the field, and in the y direction there is no variation of the field. So this is TE20 mode. Similarly for this, in x direction there is no variation of the field, and in y direction there is one half sinusoidal variation of the field. So this is TE01 mode. So this is how we can plot the field variation of any TEMN mode or TMMN mode inside a rectangular waveguide. Now let us see cutoff frequencies for rectangular waveguide in different modes. So as we have seen earlier that gamma square plus k square is equal to kx square plus ky square for rectangular waveguide. So from here we can get propagation constant gamma, which is equal to under root kx square plus ky square minus k square. From this there are three conditions of gamma. First one is if gamma is real, then beta will be 0 and gamma is equal to alpha. In this case this quantity should be positive, so kx square plus ky square minus ka square should be greater than 0. From here we can get omega square mu epsilon is less than this, and in this mode the variation of the field along z direction will be e raised to minus alpha z, and that is a attenuating field. We call it as evanescent field. Now the second case is when gamma is imaginary, that means alpha is 0 and gamma is equal to j beta, and from here this quantity should be negative. So kx square plus ky square minus k square is less than 0. From here we can get omega square mu epsilon is greater than this one, and from here we can get frequency should be greater than 1 upon 2 pi root mu epsilon into under root m pi by a whole square plus n pi by b whole square. And for this case the variation of the fields along z direction will be e raised to minus j beta z, which is a propagating wave. So for all the frequencies greater than this term there will be propagation of the electromagnetic wave. The third case is when gamma is equal to 0, that means alpha is equal to 0, beta is also equal to 0. So there is neither attenuation nor propagation of the wave. So from here make this quantity to 0, then we will get Fc is equal to this, which we can simplify as 1 upon 2 root mu epsilon under root m by a whole square plus n by b whole square, or we can write it as v divided by 2 under root m by a whole square plus n by b whole square. And if the waveguide is filled with the air, then the cutoff frequency is given by c by 2 under root m by a whole square plus n by b whole square. This is the cutoff frequency of, so this is how we calculate the cutoff frequency for different modes. Now let us see the graph of cutoff frequencies. This plot represents the cutoff frequency of a rectangular waveguide with a is equal to 2.5 centimeter and b is equal to 1 centimeter. So for TE10 mode the cutoff frequency for this waveguide comes out to be 3 gigahertz. For TE20 mode it is 6 gigahertz. Similarly for other mode we can calculate. In this the lowest cutoff frequency is of TE10 mode. So the mode with lowest cutoff frequency is called as fundamental mode. So the fundamental mode in rectangular waveguide is TE10 mode. And if we want to know the fundamental mode for TM propagation, then the lowest frequency in TM propagation is of TM11 mode. So TM11 mode is the fundamental mode for TM propagation. Now the TE11 and TM11 have the same cutoff frequency. Similarly TE21 and TM21 have same cutoff frequency. So these modes are called as degenerate modes. Now let us move on to phase constant and intrinsic impedance. So as we know gamma is equal to under root kx square plus ky square minus k square in rectangular waveguide, and for propagating wave gamma is imaginary. So alpha is 0 and gamma is j beta. So by equating this to j beta we will get the value of beta, which is equal to under root k square minus m pi by a square minus n pi by b square, and after simplifying this we will get omega root mu epsilon under root 1 minus fc by f whole square. So this is the phase constant in rectangular waveguide. Now as we have discussed earlier in a parallel plane waveguide, the intrinsic impedance for TM mode is given by under root mu by epsilon into 1 minus fc by f whole square, and the intrinsic impedance for TE mode is given by under root mu by epsilon 1 upon under root 1 minus fc by f whole square, and for a air filled waveguide it is given by this. For TM mode intrinsic impedance for TE mode is given by this. Now let us see the phase velocity and group velocity. The phase velocity, as we have discussed earlier, that it is given by omega by beta. So if we put the value of beta here, then we will get the phase velocity Vp is equal to V divided by under root 1 minus fc by f whole square. Similarly we can calculate the group velocity, which is equal to 1 upon dabba beta by dabba omega. By solving this we will get V into under root 1 minus fc by f whole square. So as we have seen earlier for parallel plane waveguide, that phase velocity decreases from infinity to speed of light as frequency changes from cutoff frequency to infinity, whereas group velocity increases from 0 to speed of light as frequency changes from cutoff frequency to infinity. But the product of these two is always a constant, which is equal to v square or c square for the air filled waveguide. This is all about the phase velocity and group velocity. Now let us take an example and see how different calculations are done in rectangular waveguide. So let us say we have an air filled rectangular waveguide named WR430, then we have to find cutoff frequencies in TE10 mode and TM21 mode. Now first thing which we need to know is what are the dimensions of WR430 waveguide. So the convention of these type of waveguides is that the dimension A is equal to number 430 divided by 100 in inches. So A is equal to 4.3 inch. Now if we have WR230, then A will be 230 divided by 100, which is 2.3. So A is equal to 2.3 inches. Similarly, if we have WR90, then A will be 0.09 inches. Now we need to convert this A from inches to centimeter. So to convert from inches to centimeter, we need to multiply with 2.54. So A will be 4.3 into 2.54 centimeter, which comes out to be 10.922 centimeter. And in general, in these type of waveguides, B is taken as half of A. So B will be 5.461 centimeter. And the formula for cutoff frequency, as we have discussed, is Fc is equal to C by 2 into under root m by A whole square plus n by B whole square for air filled waveguide. Now put n equal to 0 and m equal to 1 for TE10 mode, then we will get C by 2 into 1 by A. So 3 into 10 raised to 10 divided by 2 into 1 by 10.922. By simplifying this one, we will get 1.372 gigahertz for TE10 mode. So this is cutoff frequency for TE10 mode. In the same way, we can calculate the cutoff frequency for TM21 mode by putting m is equal to 2 and n is equal to 1 and A is equal to 10.922 and B is equal to 5.461. And after simplifying this, we will get 3.884 gigahertz for TM21 mode. Now the next question is, if the given waveguide is filled with dielectric with epsilon r 2.2 instead of air, then what will be the cutoff frequencies for these modes? The cutoff frequency for different dielectric mediums will be C divided by 2 under root epsilon r into under root m by A whole square plus n by B whole square. We have already calculated these terms, so we need to divide cutoff frequencies we have calculated earlier by under root of epsilon r only. So 1.372 divided by under root 2.2 will be the cutoff frequency for TE10 mode, which comes out to be 0.925 gigahertz. Similarly, for TM21 mode, it will be 3.884 divided by under root 2.2, which comes out to be 2.619 gigahertz. So this is how cutoff frequencies in the rectangular waveguide are calculated. Now let's move on to the applications of waveguides. There are various applications of waveguides. These waveguides can be used to transport large powers from one point to another in any system. Some applications of rectangular waveguides includes E-plane T, H-plane T, magic T, attenuators, couplers. So let's see these one by one. So first we will have E-plane T, and E-plane T, this is the port 1 which is called as E arm, this is port 2 and this is port 3. These two are called as collinear arms. If input is given to port number 1, then the power will be divided in these two ports, but the outputs at these ports will be 180 degree out of phase. As you can see from this figure, if the direction of electric field is like this, so it will propagate like this in E arm, and after this it will be divided something like this. So the direction of electric field in this port 3 will be in this direction, and the direction of electric field is in this direction. That means these two are 180 degree out of phase. You can see from this also, this is port 1, this is port 2, this is port 3, and we are providing input from this port, and the output is getting divided at this point, and the direction of the arrows at these two ports are opposite to each other. That means they are 180 degree out of phase. I have this E plane T with me also. So, in this is the port 1, this is port 2, this is port 3. So, if we provide input at this, the power will be divided in this and this, but the outputs will be in 180 degree out of phase. Similarly, the other application is H plane T. In H plane T, the port 1 is called as H arm, port 2 and 3 are called as collinear arms. If we give input to port 1, then power will be divided equally and the output powers will be in the same phase. So, as you can see from this figure also, in this is the port 1, this is port 2 and this is port 3. So, we are giving input at this port and the power is getting divided at this point and it is going in the same phase. The two outputs are in the same phase. So, depending upon our requirement of the power division, so if we want equal power division and output should be in the same phase, then we can use H plane T, and if we want equal power division but output should be at 180 degree out of phase, then we can use E plane T. Now, there is one more T which is magic T. In this, port 1 is H arm and port 4 is E arm and 2 and 3 are collinear ports. So, in this if we give input to port 1, then power will be divided equally in 2 and 3 and the outputs will be in same phase, and the port 4 will be isolated port. As you can see from this figure, in this is the port 1, this is port 2 and 3 and this is port 4. And if we give input to this port, then output is getting divided in these two ports equally with same phase, as you can see from the direction of the arrows, and the port 4 is isolated port. Similarly, if we give input to port 4, then power will be divided in 2 and 3 equally, but in opposite phase, and port 1 will be isolated as seen from this. And one more thing, if we give input at port 1 and port 4 simultaneously, then the sum of these inputs will be provided at one of these ports 2 and 3 and the difference will be provided at the other port. Now, the next application is a coupler. So, in coupler we have 4 ports: input port, through port, coupled port and isolated port. So, in this is the input port, this is the through port, this is the coupled port and this is the isolated port. This isolated port in this coupler is terminated with a meshed load. This coupler is a 10 dB coupler. So, if we give input 0 dB here, then we will get minus 10 dB here at the coupled port. Now, the next application is attenuator. So, this is the attenuator. In this is the waveguide. We will give input here and get output from here, and there is a absorbing material which will absorb the power flowing through the waveguide. This is 10 dB attenuator. So, if we give 0 dB input here, we will get minus 10 dB output here. So, this is a fixed type of attenuator. In general, the waveguides are used to transport a high power from one point to another in a system. Thank you.